Hello, doctor. I will be showing you the simulation for Mrib Lab 2. So first of all, you open this, open the app software, and then you and then you create the circuit. So I'll show you one example from the circuit, from the lab. So this is the first one. So all we have to do is build the circuit, and then make the driver. You have to compile and check and compile. So after you check and compile, you can see if there's any error here. So when the error is okay, no errors, you open this. This one is on start. So after you do that, you have to go here, communication system, choose driver 5, which I registered. Okay, then go here. This is called online mode. You have to press online mode. After you do that, yes, transfer. It'll take some time. As you can see, okay, now you can simulate the circuit. When you simulate the circuit, the light will be on. So this is how this software works. So we can even forcefully off it, on it. So when always close is open, it will stop the supply and the light bulb will not have, the light won't turn on. So this is one of the ways to force close and force open the system. Okay, now I will show you another circuit from the Mrib lab. So as you can see, all I have to do is turn it on. Yes. Transfer. Okay. Okay, so this is the circuit from 7.1.4. Then you run the simulation. As you can see, I forcefully open a few switches so the light will be turning on. So for example, if I force off this, it's already in. If I on this, the supply won't pass through, as all 3 lines from each goes to X3. So X3 plays the most major role here. If this does not transfer any supply, Y0 will never light up. So for example, if this is on, this is normally closed, and either one of this, the supply can still pass through, and either 3 of this, the supply can still pass through. So this is how the software works, and next up my my groupmate will be explaining regarding the truth table. Thank you very much.
Hi, Doctor. My name is Tung Yao Shen, and now I will continue to present for the Lab 2 MRIB. So now I will explain and show how I can test the output according to the input given using a truth table. So actually, how to test using truth table is already explained in the previous lab, but this lab I will explain more detail about how we can check our results. So we are given 5 program. For first program, 7.1.1, this is network 1, which is there is a NOT gate of X0 and a NOT gate of X1. And this is a truth table we will get, since that there is no 2 NOT gate. So 0, 0 will become 1. Since that NOT gate of 0 is 1, NOT gate of 0 is also 1. So 1 and 1 is 1. And the total number of value given obtained is 4, since that there is only 2 gates. So for the second truth table, which is a 7.1.2, there are 2 networks, which is network 1 and network 2. So for this network, the equation is like this one: X1 and X2, the output will be Y0. X3 and not gate of X4 and X5, the output will be 1. And this is the function, or we call equation. So from this equation, we can straight away substitute the value that we insert in the truth table. For example, 0, 0, 0. So you can just substitute 0, 0, 0 here. So we can see that 0 and NOT gate of 0 is 1. 0 and 1, 0. 0 and 0 is 0. So the output will also be 0. So for the first network, which has got 2 gates, so the output will have 4 only. For the second network, this is 3 gate, 3 gate. So the output will be more than 10. So I just show here it's only a 5. So for the third table, 7.1.3, so the function obtained is this one. For the first one, you can see that this is a parallel circuit here. So it is a OR gate. So usually we have to do the NOT gate of X2 and X3, first one. NOT gate of X4 and NOT gate of X5, the second one, which is here, we can see. And we use an OR gate to combine these two, and use an AND gate to combine with X1. So we get the two output, which is Y0 and Y1. For the second network, this is NOT gate of X6 and X7, which is a very normal circuit. The output will be Y2. So it's also the same. We can just put a table and set all these values first. Then we substitute inside, we will get the result. And this is the result that we get for the first network, which is the 5 result here. Because it is have 5 gates, so it will be more. So I just choose 5 only as the same. So the Y1, Y0, and Y1 will have the same output, since that there is 2 output from one circuit. And for the network 2 here, since that there are 2 gates, so the output will, the truth table will also have 4 lines. So for the 7.1.4, which is the last one, this is a more difficult circuit. The equation will be like this one. You have to do here first. For the X1 and NOT gate X2, first one. X NOT gate of X5 and X6, second one. So we have used 2 NOT gate to combine all here, which is first part or the second part or X7. It will be one after combined it. We will add an AND gate to X3. And here we also use an OR gate between X4 and NOT gate of X9 and combine it with an AND gate. So the output will be go to Y0. This is the equation. So we use as the same. We just set all the value first. For example, X1 will be 0, X2 will be 0, X5 will be 1, X6 1, X7 0, X3 1, X4 1, X9 0. After that, we can substitute inside. We can count it. You should use manually. So this is the result you get. And for this one, the result, if we calculate, it will be more than 100 over. So I just take 5 only. So actually, how I cannot confirm the answer? Usually, for me, I do that. I will do from the freehand first for first 5 or first 10. After that, I will enter the equation that I show here to an online program. For example, this is the online program I use. So here I will enter the program here. Then the result of the truth table will be built automatically here. And from here, we can know that the output will be 257 output. So I will only choose that the value that I put in the truth table and confirm here whether the output is correct or not. So this is the way that to confirm the answer. But for me, I will do the freehand first. After that, I will only combine. But some of the students maybe will straight away do that. But since that this is a lab, so I will follow the instruction to do normally using freehand first, then confirm the answer. So that's all for my part. So the next part about the observation and the question 7.2, 7.3 will be presented by my another group member. Thank you.
So for question 7.2, what will happen if the user did not click online mode when executing program? So when the user did not click the online mode, the transfer window will not pop in, as well as the program green light would not be available upon running the program. Therefore, clicking online mode is necessary before simulating the program. Next, for 7.3, modify the figure from question 7.1.3 so that lamp Y0 or Y1 will always on. So this is the before. As you can see, Y0 and Y1 is off, and after we modify the circuit, lamp Y0 and Y1 are on. For the discussion, as for question 7.1.1, when we simulate the ladder diagram, it simply turns on, as you can see in the diagram shown, stating the light turn on once supply is given. As for the remaining 4 circuits, none of them were turned on due to the NO and NC either blocking when on or off which makes the supply not travel during off nor on condition and thus not lighting up any light. And for the 7.3, we forcefully made a pass by forcing the NO and NC to on and off condition, so we were able to turn on the Y0 and Y1. So we understood the concept of how the PLC ladder diagram works, and this helps us understand how a simple PLC system works. And lastly, for the conclusion, based on the experiment, we were able to familiarize the techniques to program PLC using programming ISPsoft. ISPsoft is a software development tool for Delta's new generation programmable logic controllers, which supports 5 programming languages and a large number of applied instructions, which in this experiment we use the ladder diagram language. So in addition to the basic program function, ISPsoft also contains many auxiliary tools, and the multilingual environment and the friendly user interface provide users with a convenient and efficient development environment. That's all from us. Thank you.